Hello, this is QMG, and this is very exciting because today is about teleportation. You are going to watch live teleportation of information. So stay tuned because if you have access to the IBM quantum platform, like the one that I'm having right here, you can actually do this at home as well and get results. And I'm going to really get results, I believe. And we're going to discuss those numbers, okay? So now to begin, teleportation. Teleportation is not the same as transportation of information, okay? So in order to show you about teleportation, I started by creating an entangled state between three qubits. As you can see right here are my qubits. They are all at 0. They're all at 0. Okay, and we're going to be passing them through gates in order to see what happens. Now, one wonderful feature of the IBM quantum platform is that it allows you to get theoretical values. If you go to view and you go to the state vector, it shows you the possible outcomes that would result from this one. And there you go. Okay, as you can see, we would have 4 different outcomes. And right here, you can see all the outcomes. What does that mean? Well, you can get 0, 0, 0. You can get 0, 0, 1. You can get 1, 1, 0, and 1, 1, 1, 1. Okay, the first qubit on the left is Q2, and then Q1, and then Q0. Okay, so that way we can know what's going on. So notice something interesting. The last two can be have to be the same. Okay, and we have to be the same. Okay, just pay attention to that pattern because that's going to be important for teleportation. Okay, so every time we run this experiment, we're going to expect, with this circuit, we're going to expect Q1, sorry, Q1 and Q2 to be the same. Okay, perfect. All right, and the first one, Q0, well, that one you can get 0 or 1. All right, this is important. Pay attention to this one because you're going to see the teleportation right now. Okay, it's going to make sense in a little second. All right, just showing you the possibilities here. Now, what happens if I flip this one right here? So now, instead of being this state, we're flipping it to be 1, right? That's what the gate does. So what happens now that I flip just the first one? Well, let's take a look at our theoretical values. Ooh, there you go. Okay, so now notice we have a different pattern. The last two, which correspond to the last two, are now flip. Okay, so that they are opposite. So now Q1 and Q2 are opposite. Okay, when we started with 1. Okay, so if you think about it, we can use this information to make sure that this state appears immediately into Q2, the last qubit. So that's what we're going to do. Teleportation, we're going to use what happens to one qubit and shape the other qubit so that that information from that qubit, whether it's a 0 or 1, comes up in that one right there. Okay. Now, to make things more simple, I'm going to skip a few steps and just show you how we can do that. So basically, if we get the answer from Q0 here and Q1, we can actually shape something in Q2 to get the answer, right? So how do we do that? Well, I'm going to do a little trick right here in order to do that. And here's a nice little trick that you can try at home as well. I'm going to, the answer that comes out of here, I'm going to use this gate right here to control the answer. So this is what I'm going to do. I'm going to pull this gate right here, put it right there. Okay. And of course the answer, and we can measure the answer here and use it to change this one right here. But due to technical difficulties, I'm going to skip that one. I'm just going to leave it like this. This is good enough. Let me show you what happens, theoretically speaking, just to discuss it. So notice the answers, okay? So again, notice how the last one, by doing this, is always the same now, right? So we managed to make Q2 always equal to 1 when the first qubit entered was 1, okay? So we managed to make them the same, right? What happens if we enter now the opposite? Well, let's see. We enter now 0 here, right? So we are starting now with 0 here. What happens to the answer? Well, we expect that to be 0, right? Let's see. Let's take a look at it. State vector. There you go. As you can see now, the possibilities that we would get would be 0 for Q2. It's always equal to 0. It's almost like, as you can see, theoretically this works. Every time this one is 0, this one is 0. Every time this one is 1, this one is 1. And we're not transporting energy at all. No transportation. This is teleportation. Okay, this is a famous teleportation, but of course involves catching this at the same time in our computer. So this is a theoretical value, right? So if what we're doing is correct, it should come out like this. So how about this? Stay tuned because we can run this and see if we actually obtain the results that we expect by theory. Let me close this one right here. I just want to make a little point here. So I don't know if you notice this right here. I'm going to explain one little thing. Notice that these two are red right here, which means they are minus, okay? So we just have to remember that when the first one, the results from Q1 is equal to, when Q0 is equal to 1, then we have to change, we have to make whatever we get for the qubit the opposite, right? Change phase, okay? I'm just going to change phase, okay? And that's just a minor detail. It doesn't make a difference when it comes to measuring probabilities. You'll see, okay? As you can see, it works. You can see just the numbers. We put a 0, we get a 0. We put a 1, we get a 1, right? And when you measure probabilities, these phase differences, in this case, don't make a physical difference, right? There might be situations where they make a physical difference, but not this one. All right, so now, can we run the experiment? Oh, let's do this. So in order to run the experiment, we need to measure the information along each one of the possibilities, right? Okay. And of course, this is what we're looking at. Let's look at probabilities now. Of course, we expect 4 columns. We get 25% for each one of those possibilities, right? And if we measured, if we flip this one, we expect also 4 possibilities. Let's take a look at the probabilities that we expect. Okay, there you go, 4 probabilities. And this way, we can teleport information far, far away. That's what is very, very weird about this, because if you separate those qubits, any of these qubits, like let's say this one, if you could separate them far, far away, they still remain entangled. Okay, and you still find the same values. Okay, so how do they do that? Well, that's the mystery. This is the non-locality problem, and so that's why I guess it's useful in teleportation, right? Because you're not transporting information. Somehow the information goes from one and pops into the other one. All right, ladies and gentlemen, you're about to watch teleportation. So I'm gonna run it. As you can see, I put 8,192 times here into the Burlington IBM quantum computer. So let's run it and let's see what we get. Ooh, it's going. Let's see, jobs. I see it working. Okay, good. It's creating. So let's go into the one that we just created. Let's see, sometimes he just says create, but it already gets the results. All right, let's go into the page. This is exciting because we're about to watch teleportation. And remember, we're supposed to get, theoretically speaking, 4 columns, right? 4 possibilities. So it's still running. So remember, okay, so 4 possibilities. Now the question is, are we going to get 4 possibilities when we look at it? Because nothing is perfect. And the answer is no. We expect some errors. All right. And this is what gets my attention, the errors, the things that don't fit, because it requires an explanation, right? When the theory doesn't match the experiment, you always have to wonder, what's wrong with that? So either the conditions for the experiment are wrong or the theory is wrong, right? Or both, a little bit of both. So that's why this is very important. And you can run your own experiments. Maybe you can figure it out as well, right? As you can see, there are the circuits that we are using. So this is the circuit, and then it's correctly transpile. As you can see, we can see one and the other match pretty well. So we don't expect any problems to occur. It's still running right there. Let me go back here. Let me see. Let me try it again here. Creating. Complete. Very good. Raise yourselves. Raise yourself. Teleportation. Teleportation. Oh, look at that. My God. Look at that. Wow. Let's look at the circuits. Notice what we did. We teleported right here a 0. So we expect this one to be 0 as well, right? By teleportation. And notice right here on the top, notice something interesting. We did get that right there, right? As you can see, right here, we were able to verify that most of them actually did that, right? We can see that most of them, some of them did not, right? So we can consider this one's errors. And I'm gonna put a question mark right there. Errors. So what went wrong right there, right? And notice how this one looks kind of like going down. Well, we were expecting 4 columns, and we expect this one's to be exactly the same. Why the difference? Well, that is the question, right? That's where physics comes into place. What is going on? Certainly, we confirm that we teleported information most of the cases, but there are errors right there. What could be the source of those errors, right? That is important to know. Now remember, in order for this to work very well, you have to make sure that you can establish coincidence between events. Okay, there's got to be coincidence. So I'm going to put a question mark there. So is that a failure of finding coincidences between things? Now, how coherent, how pure were the systems, right? We don't have a pure quantum system for whatever reason, noise, you name it, then we don't expect the results to be ultimately correct, right? So we assume the theory is correct. So I suppose something in the conditions is not helping in this situation, right? So it's something to think about, but this is exciting. As you can see, I was able to teleport the 0 onto the other qubit, right? As you can see, most of those have a 0 at the end. Okay, well, we can also do that for the 1, right? Just by changing the input here, we can actually switch this around, right? We would expect this one to be a 1 right here when we measure it. So we would expect these columns to be opposite to one another. And I ran these experiments last night. I can tell you it's almost the opposite, okay? It's almost mirror. If you take a mirror, it will look the opposite of this one. So something interesting is going on here, okay? And I would like to know what it is. Well, it was fun being with you. And remember, for those about to quantum, we salute you. This is QMG. See you next time.